Okay, for part 1 of Project 7, we're going to look at reflections and symmetry. We're going to show how to create a shape and reflect it over any line. I'm going to use the X and Y axis because in the classroom that's one of the most common things that you would reflect over. And this works well if you have actual points that maybe you show them on the grid, and you can show the other points on the other side of the axis, and they see the relation. They see that everything is just a reflection over one of the axes. Okay, so the first thing we're going to do is just create a polygon. So we'll just create a simple triangle like this. And then let's say we want to reflect it over the y-axis. So we go to reflect about a line. I want to choose that polygon. I want to choose the y-axis. And I have my mirror image. Now if I move it, you're going to see that it moves as well, because just like a mirror image, if you move further away from the mirror, well then you appear further away in the mirror. Okay, so they can cross, we can move them down. But let's say we also want to talk about reflection over the x-axis at the same time. Well, you hit reflect about a line, let's choose our polygon again, and let's choose the x-axis. Let's see. And there we go. So now we also have a reflection of our original image over the x-axis, and if I want, I can show how the reflection over y and the reflection over x work, and I can even create another reflection let's see, that way. And then I can show reflections over x and reflections over y. Okay, so next what we're going to do is we're going to look at an image from nature, and we're going to see how reflections work in nature, how close we can get. Look at an image in nature and see if there's symmetry in that. So what I want to do is go to Edit, Insert Image from File, and I'm going to pick this flower, and we're going to go ahead and enlarge it. And one of the things I want to do is I want to set it as a background image. That way when we draw our trace over it, we'll see the trace on top of it. Okay, so we set it as background image. And first thing I want to do is create a line. We can just do a segment or a line, that's fine. That goes from the center out to, let's say, the edge of that petal. And so everything that we're going to do is going to reflect around this line. So I need to create a point, and I'm going to create my point. My point's going to be right there on the edge of the flower. And then, like we did before, just reflect about a line, choose my point, choose the line, and I have a point E prime that's on the other side of that. Now as we move E, you'll notice that E prime moves, but what we want to do is see how well it traces it, so we're going to go ahead and turn the trace on for both of those. And this way we can see on our flower how symmetric it is about the line that we chose. Alright, well, pretty close. We probably could have chosen a different line that goes through one of the petals that may have been a little bit closer, but just goes to show that there is some symmetry in nature. Of Project 7, what we're going to do is show how to translate an image. So I went ahead and imported an image of a motorcycle, and it took it automatically put 2 points at the 2 lower corners, so I went ahead and snapped point A over to the origin here, and point B is just here a little bit shy of 2 on the x-axis. And so in order to translate it, what we want to do is we want to create a vector. And so we're going to go and create a vector from a point, and we're going to choose the starting point and the vector. So my starting point is going to be A, oh, sorry, I need just vector, choose A, and I'm going to go ahead and move it 2 units to the right. Okay, and then what I want to do is translate it. Let's see, translate it by vector, and I just have to select the object and the vector to translate it. So I'm going to go ahead and select my motorcycle and select the vector, and it's going to move it 2 units. Okay, so that was just how to move it 2 units. Alright, okay, for the third part of Project 7, what we're going to be looking at is Riemann sums, specifically upper and lower, and definite integral, and comparing them. Okay, so most calculus students are more familiar with the left and right methods. That's one of the first things they learn when they're trying to algebraically come up with the area underneath a curve. And that algebraic method, they kind of do left and right based on the number of rectangles. And then after that, we normally teach them trapezoidal. And using the trapezoidal method, they see that they get even closer. Of course, not as close as taking the integral, but we work them up to that. So, unlike the left and right methods, the upper and lower is based on min and max. Okay, so what we have right now is that our number of rectangles is controlled by this slider, and it's equal to 1. Okay, so we look at an interval from A to B, which are the blue dots here, over here at -1 and +3 on the x-axis. Okay, and on that interval, for the upper, what it does is it goes to the highest point on the interval from -1 to 3, which is this corner here. And so because I have n, or number of rectangles, set to 1, it's going to make a rectangle that goes from A to B that's all at this height, whatever the height is at -1. For the lower sum, what it's doing is it's doing the same thing, interval A to B, but it's just going to the lowest point, the minimum on that interval, and creating one rectangle there. Okay, so you can tell that the difference is why, because according to both of these, if I was trying to find the area underneath the curve, well, according to the upper sum it's 18, but the lower sum is 3.46, so they're nowhere near. So what we know is that when your ends are small, when your number of rectangles are small, the less accurate it's going to be. The whole idea behind integration is that our number of rectangles go to infinity, and by doing that we get an accurate number for the area underneath the curve. Okay, so let's say we go to 2. Well, then you can tell that I've divided this up into 2, with my point being here at +1. And so now from -1 to 1 it looks for the highest point, which is still here, and does a rectangle there. And from 1 to +3, the highest point is going to be over here, and so it does one there. So now my upper sum has actually decreased to 15.42, and the lower sum has increased a little to 4.73, because now I have a little bit more area that I'm covering in here. Again, not very accurate. The difference between these two is 10.68, and on something this size, that's really not acceptable. So what we want to do is just keep increasing the number of rectangles. And as we do, you can see that the upper sum is decreasing and the lower sum is increasing. This difference is getting smaller between the two. Okay, reason is because now on each one of these intervals, I just have a rectangle that goes outside of it, a rectangle that's totally inside of it, and the difference between those two rectangles is getting smaller each time. You can notice on some points like that, or down here, where there's a very small difference. So the trick would be keep increasing the number of rectangles, and we have this slider just set to where it goes to 50. So if we increase the slider all the way to 50, so we have 50 intervals, our changes, our rectangle widths going from -1 to 3. Our upper sum is dropped all the way down to 8.94, and our lower sum's gone to 8.4, which because of the decimals that it carries out, the difference is actually 0.53. Okay, that's something more that we can live with, is a smaller difference like that, numbers that aren't too far off. Now we know that it has to be somewhere between these two. The upper sum is always going to be an overestimate, the lower sum is always going to be an underestimate, just because of the fact that lower sums are never going to go above the line, upper sums are never going to go all the way below the line. Okay, so what we have here is the actual integral. Okay, the actual integral from -1 to 3, which is our a to b, it's a definite integral, for this function is going to be 8.67. Well, think about it. 8.67 is going to lie somewhere about the middle of 8.4 and 8.94. Okay, in fact, I mean right about the middle of those two. So Riemann sums are a good way of algebraically showing your students how you can arrive at a integral, or basically how we do it. Now, of course, the integration method is going to be exact, but at first they may not understand that concept. So as you're moving them from pre-cal to calculus, an algebraic way of showing them how to do that may come in handy. Now, I did it in school, but as far as getting the kids to actually calculate the area of 50 rectangles, that may be a little bit time consuming. That may be why you may want to use a program like GeoGebra to actually demonstrate that, so that they can see the difference in areas as they increase or decrease the number of triangles and how accurate you are. So of course, if we increase the number of, or not triangles, rectangles, so if we increase the number of rectangles that we can have to 100, these two numbers are going to get closer together, there's going to be less of a difference, and eventually, as this number goes to infinity, both of these are going to start approaching the integral 8.67. Alright, so that's how you can use GeoGebra to show how upper and lower Riemann sums work compared to the actual definite integral.